And some time back, perhaps nearly 10 years ago now, I started pointing out that actually, by the time we had achieved this 30-year increase in healthy human lifespan, we might actually have done the hard part of getting to an indefinite human lifespan. And the concept that I put forward was, well, it's illustrated here. On the red line here, we can go, the red line is simply a depiction of normal aging. And of course, this diagram is extremely schematic, and I don't want to take away anything too quantitative from it. But the red line denotes normal aging. We've got, obviously, age on the x-axis, and on the y-axis we have reserve, which is simply the reciprocal of damage. It's the amount of damage, additional damage that you can afford to accumulate before things start going wrong. So the pink line denotes what I've told you so far, that we ought, within the next few decades, to be able to take middle-aged people and fix them up reasonably well, so that they are rejuvenated to a biologically younger age. And then after that they age as normal, and the same slope as normal, because we're not, as I mentioned, we're not proposing to alter the rate at which damage is created by metabolism. But of course we can then apply the therapy multiple times and extend the degree to which we postpone the pathologies of old age. However, as you can see, the interventions experience diminishing returns. Eventually we get the pathology of old age anyway, as denoted by the dotted line, the black line here. And that's simply because, as is illustrated on this picture, the difficult damage, so to speak, the damage on which the therapies do not work, is accumulating unabated, and eventually on its own, however well we're fixing the easy damage, the difficult damage will knock our hero over the frailty threshold. So then the question is, can we avoid this? And I believe we can. I believe that all that's necessary is to achieve a continued improvement in the comprehensiveness of these therapies so as to stay one step ahead of the problem. And that's what's denoted by the yellow line, the orange line. If we look at what happens to this person the second time they get rejuvenated, and if we presume that the distance between these two interventions is perhaps 15 or 20 years, which seems quite likely, then we can assume that there will have been a significant amount of progress in improving the therapies, so that not only will they work on the same types of damage that they used to work on, they'll also work on some proportion, let's say half, of the damage that the therapies did not work on 15 years or 20 years previously. And so as you can see here, the result of that would be that the individual, even though they are 15 or 20 years older chronologically than they were the first time around, will actually achieve a younger biological age than the therapies were able to do the first time. And if we continue that concept, we'll continue to improve the therapy by a respectable amount every interval, then you can see that the individual continues to get biologically younger as they're getting chronologically older, however long you go out. They stay indefinitely way above the frailty threshold, and therefore they are not subject to any risk of death from aging, only from being hit by trucks or asteroid impacts or going up in a space station that doesn't work. So basically, that's what I proposed, that actually once we had made the first step in producing reasonably comprehensive rejuvenation therapies, we might actually find it rather straightforward to stay one step ahead of the problem and give the beneficiaries of those therapies an indefinite healthy lifespan. So of course the question then is, can we? How fast do we need to actually be improving these therapies in order to have the long-term trend be upwards rather than downwards? And is that rate of progress plausible? And that concept is so important, that rate of progress, that minimal rate of progress that allows the long-term trend to be upwards, that I decided to give it a name, and I called it longevity escape velocity. This is, in words, what it means, the rate at which these rejuvenation therapies need to be improved in their comprehensiveness following the achievement of this first generation set of therapies that I've called robust human rejuvenation, in order to outpace the accumulation of damage that the therapies don't yet work on, to stay one step ahead of the problem. So it's very, very verbose when you see it written out in in words, but it's a very simple concept from the graph. So then, can we do it? Well, I think there are various ways to address that question. One way that I worked on a few years ago is to simulate the process of aging and the accumulation of damage and its effect on mortality rates. And that's what we did. And this is basically what we got. The black line on the left-hand side here is a survival curve of a regular normal population that is not receiving rejuvenation therapies of any sort. I think we took Americans in 1999 or something like that. And a survival curve is simply a plot of the proportion of a cohort of people that are still alive at any given age. So, of course, by definition, the cohort is all alive at age 0, and not many of them die until age about 50 or 60, at which point they start dropping like flies and hardly any of them get past 100. So that's the black line. The dark blue line is the survival curve in the simulation of a population that has the same intrinsic rate of aging and risk of mortality from aging as the black line, but from the age of 80, they start receiving the first generation of rejuvenation therapies. And as you can see, it doesn't do them much good. It does a little bit of good, some of them, but not very much. Of course, half of them are already dead by the time the therapies arrive, by the time they're 80, so that's why the two lines are coincident down there. And then the best that you can achieve is maybe 10 or 15 additional years, because these people are frail. And being frail, of course, is risky. The only way we're ever going to extend lifespan is by extending healthy lifespan. And I always have to point out, and I'm pointing out increasingly aggressively these days, as some of you may have noticed, that I don't actually work on longevity. I work on health. I work on stopping people from getting sick. And the longevity benefits that will accrue from that are simply a side benefit. It doesn't mean I don't care about longevity. I think it's a very good thing that people will live a lot longer, especially when they're healthy, but I do not regard it as what I work on. I work on stopping people from getting sick. Okay, so that's why the blue line is not very impressive. But then look at this sky blue line here, this grey line. What's going on there is a simulation of a cohort that start getting these therapies just 10 years earlier, at the age 70. And as you can see, 10% of them manage to be rejuvenated thoroughly enough that they end up eventually completely escaping any risk of death from aging. That's why the line goes completely horizontal before we get to 0. If you're 60 years old when the therapies start, then nearly half the people manage that, and so on. And the real important thing about this graph is that I was ludicrously, insanely pessimistic about the parameters that were assumed for this simulation. Specifically, I said that we would assume that the therapies were doubled in their comprehensiveness only every 42 years. Now, I mean, that's an absolutely insane, crazily pessimistic rate of progress in my view. That's the difference between the date at which Lindbergh flew across the Atlantic and the date at which Concorde first flew across the Atlantic, which is, you know, a bit more than a doubling. And I think it's reasonable to look at past technologies for guidance as to the likely rate of progress in future technologies. So I think that's a pretty solid argument for why it's realistic that we will actually achieve longevity escape velocity.